Hi. In this lecture, we're going to talk about fitting lines to data. So remember in the last lecture we talked about simple linear models. Well, when I was drawing those lines through the data, the question is, how do you do it? How do you draw the best possible line through the data? That's the focus of this lecture. So let's step back for a second. Remember, when you did the categorical models, we had that notion of R squared, which was the percentage of variation that you explained. So there's a lot of variation in your data. You construct a model, and you ask, what percentage you explain. So for example, if I have a bunch of data like I have here, these are all the dots, right, the data. If I just took the mean of this right here and then ask how much variation there, I'd have to take the distance from all these points to the line. There'd be a lot of variation. When I draw the line through here, I explain a lot of it. And in fact, here it says I explain 87.2%. So what we want to do is we want to talk about how do you draw a line through this data to explain as much variation as possible. So remember in our box example, just to give us a reminder of how this worked, there was 53,000 units of total variation, and we only had 5,200 left. So 5,200 over 53,000, which is like 9.8%, is how much we had left over. So that means that we explained 90.2% of the variation. We want to show how you can do that same sort of calculation with lines, and then show how you draw the best possible line. So let's suppose I got a bunch of data here. To figure out how much variation there is, I draw the mean. And then I can figure out the distance. So if the mean, let's say, is 6, and this has a value of 4, I would take 4 minus 6 and square that, which is 4. And if this is the point and has value 8, I would take 8 minus 6 and square that, and that would also be 4. And I add up all those variations. That gives me the total variation. Then what I'm going to do is I'm going to line through the data and figure out now just what's the distance from the line, and ask how much of the variation did I explain by drawing the line through. So let's do a very simple example. Let's suppose I've got 3 kids, and they're different grades of school, and they wear different size shoes. So what I'm going to do is I'm going to predict shoe size as a function of the grade they are in school. So I'm going to say that your shoe size is a function of what grade you're in. So I've got a first grader who wears a size 1 shoe, a second grader who wears a size 5 shoe, and a fourth grader who wears a size 9 shoe. And I want to try and fit a linear model to this. So first I can ask is, what's the variation? So this is the grade, and this is the shoe size. Now, I don't care about the variation in the grades. I'm caring about the variation in the thing I'm trying to explain, which is shoe size. So it's just this. So it's just this 1, 5, and 9. So if I take 1, 5, and 9, if I add those up, I get 15, and divide by 3, I get 5. So the mean is 5. So to get the variation, I take 1 minus 5 and square it, which is 16. 5 minus 5 and square it, that's 0. And 9 minus 5 and square it, that's also 16. So the total variation is 32. So what I want to do is I want to write down a linear model that can explain as much of that variation as possible. Well, let's start out with just a really simple linear model where we assume y equals 2x. So if I take the line y equals 2x, what I'm saying is all 3 of these points should lie on the line, right? And so the variation is just sort of how far off the line they lie. Well, so how do we do it? Well, I've got x and y, and 2x would be 2. When x equals 1, 2x would be 2. When x equals 2, 2x would be 4. And when x equals 4, 2x would be 8. So these are my predictions in a way, right? 2, 4, and 8. And what I can ask is, how far does the data lie from those predictions? So here, I predicted 2, and the actual value is 1. So I get 2 minus 1 squared, which is 1. Here I predicted 4, and the actual value is 5. So I'm going to get 4 minus 5 squared, which is 1. And here I predicted 8, right? And the actual value is 9. So 8 minus 9 is also 1. So I get 1 squared. So the total amount is 3. So I think, wow, that's great. I started out with a total variation of 32, right? And now I've only got 3. So if I want to figure out my r squared, I just say that's 1 minus 3 over 32, right? And once again, I'm going to be over 90%, right? It's like 90 plus %, right? So that's really good. I've explained a lot of the variation. But the thing is, this was just like, I just made this up. This y equals 2x. I just drew this line. So how would I draw the best line? Well, what I can do is I can say, well, let's suppose I drew the line y equals mx plus b. So this is just an arbitrary line. And then I want to ask, how far off would that line be from the data? Well, when x equals 1, my prediction would be m plus b, and the actual value is 1. So my error is going to be m plus b minus 1 squared. When x equals 2, my model is going to say that the value is 2m plus b, and the actual value is 5, so that's going to be my error. And when x equals 4, this is going to be my prediction, this is the actual value, so this is going to be my squared error. So if I want to know what the total error is, I just have to multiply all these things out. So m plus b minus 1 squared is going to be m squared plus 2mb plus b squared minus 2m minus 2b plus 1, right? So that's a really complicated thing. And I can do that for each of the other two as well, right? So I get these long equations. Now if I do that, I'm going to get, here's my total error. Right? So this is if I choose the line y equals mx plus b, this is my error. Well, what you can do, and this is what's great about calculus, you can do math and just solve for this. Find the b and the m, right, that make this the smallest possible number. And if you do that, you choose b equals minus 1, and you choose m equals 8/3. So this is how you draw those lines. You basically go back, right, and just say, well, let's take any line, y equals mx plus b, figure out its distance to the data, right? Add up your total distance right here. So this is just the total distance or the total variation, right? And then you want to choose an m and a b that make that as small as possible. And it turns out the way to do that is to choose b equals minus 1, and this should be a lowercase m, right? M equals 8/3. Now when we do that, what we're going to predict is that when x equals 1, our model now says y equals 8/3 x minus 1, right? So when x equals 1, we're going to get 8/3 times 1 minus 1, so that's going to equal 5/3, right? So and the actual value is 1. So if we look at the difference, right, between our prediction and the actual value, it's just going to be 2/3, right? So we're going to get, the contribution to r squared is going to be 2/3 squared. When we look at 5, when we take x equals 2, the real value is 5. Our model, if we plug it in here, is going to give us 13/3. That's also off by 2/3. And if we look at when x equals 4, our model gives us 29/3. The actual value is 9, which is 27/3. That's also off by 2/3. So what we're going to get is our total variation left over is 2/3 squared plus 2/3 squared plus 2/3 squared. So that's basically 4/3. That's going to be, well, it's going to be 4/9 times 3, which is 12/9, which is 4/3. So now if I want to know what's my r squared, right? Well, if I erase all this stuff for a second, right? What I get is that how much of the data did I explain? Right? I have 1 minus 4/3 over 32. And so now I've explained, over 95% of the data. So by sort of figuring out what the optimal B and M are, I can even do better, right, than I could by just sort of trying to draw that line of y equals 2x. And so if I draw that actual line, it goes like this, and you see it becomes incredibly close to the data. So let's move on and think about how do we do this with multiple variables. So supposing instead of having one variable, I've got a bunch of variables. So now I can write y equals ax1 plus bx2 plus c. So now instead of just one independent variable, I've got two. So when you look at these things, the sign tells you does y increase or decrease in x. The other thing that regressions will tell you is the magnitude. How much does y change as a function of x? So let me talk about why this then is so important. Again, we often just reason by the seat of our pants. And so let's suppose you care about, and again, I'm going to talk about this a lot because it's just an easy and important thing to talk about, school quality. So I've got a bunch of test scores from kids. And I also know this is like an achievement test score. I've also got IQ test scores, which basically tell their innate ability in some level. Then I've got measures of teacher quality and class size. Well, what I can do is I can run a regression that says, well, the performance on this test is going to be some coefficient, just some intercept, plus some coefficient on teacher quality, on IQ, teacher quality, and class size. And what you'd expect is the coefficient on class size to be negative, right? You'd expect the coefficient on teacher quality to be positive, and the coefficient on IQ to be positive. Now, without running a model, we don't know which ones of these things are big, and we even don't know if our intuition is right. Well, let's look at class size. So recently there's been like 78 studies of class size. 4 of these show a positive coefficient, right? 13 show a negative coefficient, and 61 show no effect. Right? So this is the result of somebody did a summary investigation of 78 regression studies, data studies on does class size matter, and what you find is that only 13 times does it have that expected negative effect, and 61 times it has no effect, and 4 times it actually goes in the wrong direction. So even though we think class size matters, right, and it should matter, smaller classes should lead to better performance, it doesn't always work out that way. What about teacher quality? Well, there's a recent study by a bunch of economists, right, and they basically showed that a good kindergarten teacher is worth $320,000. Right? If you have 20 students, it turns out that those students can expect to make $16,000 more in lifetime earnings by having a really good kindergarten teacher as opposed to a bad kindergarten teacher. So again, by plugging all this data, we all expect, right, class size should matter, right, lower class sizes should be good, and teacher quality should matter, better teachers should be good. But what you find when you run the data is that class size doesn't seem to matter that much, at least in the ranges in which we're playing, but teacher quality matters a lot. So what do we learn from all this? What we learn is there's a lot of data out there. One thing you can do is you can fit that data to linear models. What linear models will do is they'll explain some percentage of the variation, maybe a lot, maybe a little. These linear models will also tell us the sign and the magnitude of coefficients. So it'll tell us whether a variable has got a positive effect, whether it's got a negative effect, and it'll also tell us sort of how big that effect is. And that allows us to make policy choices, investing in things like teacher quality as opposed to class size because they have a larger effect. This is what I call big coefficient thinking. Thank you.